In this video, we're going to discuss metallic compounds that involve the combination of two or more metals. The general term for compounds of this type is alloy, and you probably have experience with alloys in everyday life. Substances like brass, bronze, and stainless steel are examples of everyday alloys. We classify alloys into two broad categories depending on whether they are homogeneous or heterogeneous. A homogeneous alloy is what's known as a solid solution, and as we'll see in a bit, we can think of one of the metals as dissolved in, quote-unquote, the other metal. So it's a solution, it's just a solution involving a solid solvent and a solid solute. We can also think about intermetallic compounds, which are more heterogeneous and are characterized by a crystal structure that is unique to the intermetallic compound. So in the solid solution case, we have crystal structures that are identical to the separated components. In an intermetallic compound, we get a new kind of structure entirely. Within the solid solution category, we can further classify alloys into either substitutional or interstitial categories, and we'll see what these terms mean in a second. So the first category of alloys are these homogeneous solid solutions. We classify these as either substitutional or interstitial. A substitutional alloy involves substitution, makes sense, of one of the atoms in the crystal structure of the solvent metal, quote-unquote, with a solute particle. So, for example, let's imagine that we have a crystal lattice involving some of these blue metallic atoms that looks like this. In a substitutional alloy, certain atoms simply replace or substitute for the blue atoms, and these are our quote-unquote solute atoms. They may do so in a regular pattern or they may do so somewhat randomly, but the key point here is that they actually replace in the crystal lattice the blue metal atoms. Now, this can only occur under a couple of specific conditions. There are two important conditions that we need to keep in mind here for substitutional alloys. The first is that the two metals must have similar radii, so that the solute metal can replace the solvent metal without a large disruption to the crystal structure. The second condition is that the two metals must have similar bonding characteristics. And by this we mean that they should form the same type of crystal structure so that, again, introduction of, for example, a red metal atom doesn't disrupt the crystal structure of the alloy substantially. A great example of a substitutional alloy is 14 karat gold, which in fact is not pure gold, it's actually a solid solution, a substitutional alloy containing silver atoms in the crystal structure along with gold atoms. The fact that silver and gold are in the same group and their similar atomic radii means that silver can easily replace gold to form this substitutional alloy. In interstitial alloys, the solute metal atoms occupy interstices or interstitial positions in the crystal structure of the solvent metal. Interstitial positions is really just a fancy term for holes or empty spaces in the crystal structure. These holes are a natural consequence of the fact that the metal atoms are spherical, and provided the solute metal atoms are small enough, they can fit into these empty spaces between the metal atoms. The result is an alloy that's not a substitutional alloy, since nothing has been displaced per se from the crystal structure, but an interstitial alloy in which the red metal atoms have kind of snuck in between the blue solvent metal atoms. The key condition here to form an interstitial alloy is that the solute metal atoms must be much smaller than the solvent metal atoms. In fact, they need to be small enough that the crystal structure of the solvent metal atoms is not disrupted significantly by the introduction of these atoms in the interstices. A great example of an interstitial alloy is steel. In steel, the solvent atoms, that is, the larger atoms that form the broader crystal structure, are iron, and the interstitial atoms, which are much smaller, are carbon. If you think about the positions of carbon and iron on the periodic table, you can rationalize why this very small carbon atom is able to fit between the iron atoms in the crystal structure. Those carbon atoms form additional bonds to the iron centers, creating a stronger lattice overall than, for example, the pure iron metal. In some cases, when a liquid mixture of metals solidifies, the resulting alloy has a different crystal structure, a different type of lattice than the separated solvent or solute metals. The resulting compound in that case is known as an intermetallic compound. It's not a solid solution because the metal's crystal structures are completely different in the intermetallic compound than they are in their pure form. If you think back to what we just looked at with the solid solutions, the crystal structure of the solvent metal remained more or less the same. We just either substituted or inserted solute metal atoms into the structure. In an intermetallic compound, we end up with an entirely new crystal structure. A nice example is brass, and I won't draw this out. All I'll say here is that brass is an alloy containing copper and zinc, and the crystal structure of the brass itself involves a body-centered cubic structure, or BCC. However, the pure copper and zinc metals have a totally different crystal structure. The copper assumes a cubic closest packing, or CCP structure, while the zinc assumes a hexagonal closest packing, or HCP structure. The combination of the two metals under high temperature and then resolidification produces this brass alloy with a totally different crystal structure, BCC.